Hello. So, welcome to lecture 4. Now, if you recollect, in the last class we were talking about lastly we were talking about embodied energy, and talking about before that we talked about that's what the energy we talked about, and but right in the beginning we talked about eco footprint, and I said that we will look into the calculation sometime. So, let us look at today first the calculation part of it, then again we will go back to the material, right, and we said it is cement which is the major contributor to greenhouse gas emission after fossil fuel. So, we will start with cement, right. So, this is what we will discuss today, calculation of ecological footprint, how do they do that, and cement, because if you remember it is done for it can be done for individual, but to a nation or for the whole world. So, essentially basically it is a biologically productive area used to produce the resources consumed, total. That is what we defined it earlier. I am just giving brief again, and we defined something like biocapacity. Recollect that we talked about biocapacity as well, or biological capacity, which is the capacity of the ecosystem, right, to produce useful biological material and to absorb waste material generated using current technology, right. And this ratio gives you, basically this ratio gives you whether, how many planet equivalent you are using, number of, if you recollect we talked about that sometime earlier. So, biocapacity is one thing, ecological footprint is a other thing. This is what ecological footprint of all the activities that you do, and biocapacity is what is available, right. So, remember that we said that you might require 3 planet right in 2050 if you go in the same manner as you are consuming. So, this is this is based on basically biocapacity for using current technology, etc., used for human economy of given year. If you recollect, it was given year also, because it will change from year to year, both biocapacity or technology will change, and I gave example of Malthus population, agricultural food generation is in, I said it was in AP series, population growth in GP series, but then he thought that the society is not sustainable, but the food production went not in AP series, it improved much better because of agriculture, technological change and all. So, also new land might have been brought into agricultural fold and so on. So, biologically productive area is essentially the land and water, both marine and inland, that support significant photosynthetic activity. Remember, I said that it is plants which captures the carbon, right, takes the carbon dioxide from the atmosphere, convert them into carbon, which is a courier of energy. So, it is mainly the plant. Therefore, those area where photosynthetic activity goes on, right, which supports significant photosynthetic activity and can cause biomass accumulation. Carbon, it captures the carbon, so therefore creates a biomass, it accumulates biomass that can be used by human being. Obviously we are talking mostly, because we said that in this calculation we are not even thinking about the wildlife and such things. Whatever is captured, even if we can, human being consumes all, that is what we are looking at. So, basically biomass, the area which can accumulate biomass, that is what is the biologically productive area, So, there is an equivalence of everything. So, net biomass productivity is the difference between gross productivity, that is production of plant material by photosynthesis, but then some of the energy is used up by the plant itself, right. Some of the carbon dioxide is released by the plant itself, all right, because of its respiration process. So, net is the difference between the two. so long as the capture or the carbon dioxide it captures through photosynthesis is more, then that is lost by respiration, plant will survive, right, plant will grow. So, net productivity is the difference between the two. And primary production is the synthesis of new organic material, that is what it does from inorganic molecules such as water and carbon dioxide, that is what it uses, the plant uses, or chemosynthesis, photosynthesis or chemosynthesis, respiration consumes a small amount of energy. So, therefore, the area which is bioproductive, that we can identify, right, and that is what goes in calculation. So, that is what, for example, net productivity, if one looks at tropical forest, that has got very high value relative to, let us say, desert. Let us say desert, temperate grassland, tropical savanna, temperate forest, boreal forest, etc., etc. So, different types of forest and such lands can actually their net productivity we know, and they are essentially the biological product. Other things are converted into equivalent of that. All other things are converted into equivalent of that, right. So, mean productivity per unit area, that is why this is given in dry grams per square meter per year. This one is given in dry grams of the biological material, that is carbon, biological material, that is carbon, that is what is given, grams per square meter. So, biomass generated per meter square per year. So, that is an example. Two more terms we got to define. One is called equivalent factor, and these values which I will give you, some data I will give you, this is from 2003. I gave you some data of 2008. So, this is various agencies actually they do these statistical calculations, and like United Nations agency, various agencies they do this, and obviously individual researchers also do. For example, I could lay hand on papers from China, some from England and so on. So, they did for their and I am sure there must be something available, if not research article, but something must be available on the Indian data too, because you can get the data, but somebody may have to analyze. So, there is something defined as equivalent factor. Now, what is equivalent factor? It is the ratio of productivity ratio of productivity to average biomass, ratio of productivity to average biomass product, that is translate the specific land type. So, it considers 5 type of land. When we look at the biocapacity, we consider 5 type of land. What are those? Cropland, pasture, forest, fishing ground, these are the 4, but there are, for example, this will have marine and inland water. So, they will break this into 5, and this is this ratio gives you universal unit of biologically productive area in terms of global hectare. Okay. So, it is productivity of a particular land or particular type of land area divided by average productivity of all types of land mass, for all type of land mass, right. So, for example, if it is a cropland, this area type, right, if I divide for all the land area, find out the productivity of biomass, productivity of all the types of land area, divide by the area itself, then I get average productivity per unit area, average productivity per area. And now I take productivity of cropland alone, because we have seen the productivity varies with the type of land. For example, this is in tropical forest, this is somewhere in desert. So, its productivity is in terms of grams per square meter per year is much higher, biomass productivity, compared to desert, which is very less, right. It is of the order of 2000, where this might be of the order of around less than 100. So, biomass productivity of land varies. Now, I want to convert them into a relative factor, and that relative factor is equivalent factor. That relative factor is equivalent factor. So, equivalent factor is the productivity to average biomass productivity, biomass productivity to of that particular type of land to average biomass productivity of all types of lands that we have, right. So, this all specific land type, it converts into a number, some factor. For example, then if I know how much cropland I have in the country, how much desert I have in the country, I will multiply by that factor to get the weighted area. So, cropland etc., etc. So, this is how it is. So, a cropland is 2.21 global hectare per hectare of overall, because average it was it is the ratio biomass productivity. So, global hectare per hectare. So, 1 hectare average corresponding to the for cropland, it will be 2.21 times of the average 1 hectare productivity. Grazing land 0.49, forest 1.34, inland water 0.36, because the aquaculture, fish, and also I mean basically biomass we are looking at. So, as far as the algae and such thing whatever grows there, this is what it will look into. So, marine same, and built areas taken is also same as this. An assumption is made here that built area would have been constructed on cropland, that kind of fertile cropland only. Civilization wise, civilization grew, civilization grew mostly in the near the river, fertile land, etc., etc. So, it is thought that it is this cropland which was converted into built area. So, built area is given the same. So, as far as this is the equivalent factor, right. Now, this equivalent factor of course are only for 5 types of land, as 5-6 types of land. This is what is taken into account. I mean these two are together, but then they are divided into 2 parts, they are also similar. So, this is used in calculating biocapacity of a country, the urban area or whatever you consider, some area biocapacity, obviously urban area this will be maximum. So, biocapacity you calculate it for biocapacity for any area, country or globe as a whole. While ecological footprint is what we are consuming, biocapacity and ecological footprint. So, ecological footprint takes into another type of land into account, which is called carbon land. Right. Now, carbon land means this gives you the bioproductive area required to capture all the carbon dioxide that is produced, right, all the carbon dioxide that is produced, that is what is the carbon land, because carbon dioxide is generated, that would be captured or assimilated by the plants. So, you need some bioproductive area. So, one can calculate out, because on an average basis, of course, this I am just giving you introduction, this could be a very several things are not done. If you want to do actual calculation for a given country, several things are also to be done, because you are importing, exporting, tourism, these are some details and there are more complications involved. So, I am just giving an introduction, because it is not course exactly on ecological footprint alone, but this introduction is important, because to understand that carbon issue is absolutely important. So, you can see that ecological footprint involves carbon land. If you are generating carbon dioxide, how much land, because there is a natural cycle, beyond that there can be an imbalance of the carbon dioxide, which I talked about sometime earlier, right. So, how much land do you require, biologically productive land, which can be used, which will be useful for photosynthesis to capture all the carbon. So, carbon land required for this area, geographical or political geographical area, nation, etc., you can find out. So, biological productive area required to assimilate the carbon dioxide or carbon generated. So, that is what it is. Then we define something called yield factor. So, we define something called equivalent factor, we defined yield factor now. What is yield factor? Not all the lands have, all the cropland do not have the same kind of same value. 2.21 was an average for the whole globe, but some countries cropland may produce somewhat less compared to another country, or some countries grazing land might produce more compared to other country. So, yield factor takes account of that sort of situation. So, yield factor account for different production of given land type across different nations, right. For example, same type of land in two different parts of the world might be more productive or less productive. Relative productivity of two different same type of land in two different countries might be different, and this is taken care of through yield factor. So, for example, this is what is the excuse me, yield factor for certain countries. Obviously, how it is defined? World average is taken as 1 for everything, right? World average is taken as 1. For cropland, world average is 1. Some country will have 0.6, that means for the same area it produces only 60%, it is 0.6 times of the yield for the same area, or per hectare production biologically or production of biomass is 0.6. It would depend upon climatic condition, also technological scenario as well, depending upon all. So, for example, Japan is 1.5, Laos I did not have the Indian data available, New Zealand they have 2.2, and Guatemala is 1. So, it is close to 1 average. If you see the grazing land, New Zealand is 2.5 because they produce milk, and maybe Switzerland, if you look at it, it will be pretty high, all your many chocolates coming from there. So, grazing land, their milk production is very high milk. So, grazing land they utilize it, and the productivity is higher. Forest, their forest also, this is what they utilize, but then marine and fisheries they are very low, whereas Japan this is relatively high, 1.4. So, country wise then the yield factor is related to country wide situation. So, based on that one can calculate, right. So, the equation will be something like this: eco footprint would be, this is yield, and this is equivalent factor, right. This is the total amount of ith type of product that you are considering. Now, two difference is, when you are finding out biocapacity, you will not take the carbon land. Biocapacity you will not take the carbon land. In eco footprint you will take the consumption. Biocapacity you know the land area and find out the total biocapacity available, right. Eco footprint you will also take the carbon land area and you take the consumption, right. So, Ti is the consumption, eco footprint, EEF is the eco footprint, TF is the annual amount of ith product consumed, right. Yi is the yield factor, because for the country we will have a break. So, we will have a break sometime, then we will go into bigger discussions, right, no problem. Yield factor is 1 for the world, ecological footprint should be lower, is not it. Ecological footprint, I am not talking about the capacity, I am talking about the ecological footprint. If I have higher yield, that means my land is more productive, eco footprint is less. That is why it is divided, multiplied by equivalent factor. What is equivalent factor? Because the type of land I will take it, production of a given type of product in a type of land, I mean corresponding to those type of land, how much is right, how much I am producing annually. As I said that I might import something, export something, there are more complications involved, this I have not taken into account. I mean they are bigger, the mathematical treatments, algebraic treatments are much much elaborate. I have just tried to give you simple examples or simplest situation. So, Ti divided by Yi into equivalent factor, sum up for all the things, right. So, that will give you the ecological footprint. It is the consumption that I am looking at, annual amount of ith consumed, ith product consumed from a given type of land, and then summing up for all, because there are 200 types of products that has been actually, or more, large number of products that has been. So, it becomes more elaborate. I am just trying to show you the simplest of the formula. So, that is how one calculates the eco footprint, right. So, what all you got to know is, for example, you got to know the yield factor for the given country and equivalent factor for given type of land, product and land and so on. So, therefore, this you can. So, this is what equivalence factor, that is what we had, equivalence factor, that is what we had earlier, equivalent. Yeah. So, this is what we talk about, right. Now, if we take example of 2003 that was available, there are 11.2 billion hectares of biologically productive area in the world, right, corresponding to roughly about 1/4 of the planet's surface. We know that 3/4 is sea, marine environment and all that. Actually, out of which 2.4 billion hectares of water, useful water was there, and 3.4 billion hectares of grazing land, 3.7 billion of 8.8 billion of hectares of land in the that 11.2, 2.4 billion hectares of water, inland water, 8.8 billion hectares of land, which involves 1.5 billion hectares of cropland, 3.4 billion hectares of grazing land, 3.7 billion hectares of forest and 2 billion hectares of built up land. So, you can sum this up, 8.8 plus 2.4 makes it 11.2, right, and 1.5 plus 3.4 plus 3.7 plus 0.2 would make it up to 8.8, because this is 7.1, 7.3 plus 1.5, 8.8. So, this is what, right. Population of the world was 6.3 million, billion at that point of time. Therefore, 11.2 divided by total biologically productive area is 11.2, population is 6.3. So, this ratio is 1.8 global hectare is the capacity per person, right, capacity per person, and this capacity is fixed, as opposed to that the eco footprint would be different, that depends upon consumption. So, this is biologically productive area was this much, right, per person was available was this. So, if you look at world ecological footprint biocapacity in 2003 in gigahectare, we had cropland, which was how much was the cropland? 1 billion hectares, 5 billion hectares of cropland, multiplied by the equivalent factor, right, because how much compared to the average, that is. So, this you will get from the biocapacity, ecological footprint of whatever you have consumed, how much cropland, from that you can actually find out consumed divided by yield, etc., for all. So, this grazing area was this much, and as far as footprint is concerned this much. Carbon, of course, it is not there, it is only here, and sum total comes out to be 114.0, etc., more or less, because some rounding is there. So, it comes out to be this, and ratio therefore is 1.26 planet equivalent. So, I just showed you a graph. I am just showing the simple way to calculate this. If you want details, there are of course literature available, lot of literature available on this aspect. So, this is how they actually arrived at different planet equivalent. I was talking about that we are spending around 1.5 planet equivalent in 2010, and if the rate it goes out 2050 you will require 3 planet equivalents, all right. So, that is what it is. So, that is how we do the accounting, that is why we do the accounting, right, that is how we do the accounting. So, after that now having looked at that, we can now look into materials back again. So, I just wanted to show you an example calculation, because I told you the theory earlier, but the example calculation I just wanted to bring in. So, now the materials, first of all, because we said that embodied energy, operational energy, all this we have discussed in the last class, and we said the carbon issue is important, life cycle issue is important, that is what we looked into. And now further we understand why carbon issue is important, because more carbon you generate, you need more biocapacity to absorb it, which is not there. So, if you want to live within the means of the planet and make it sustainable, we have also defined sustainability earlier. So, then you need to look into like this look into this carbon aspect. So, cements obviously carbon aspect is one of the more important thing, and because we are looking at those materials. So, cement of course is main, then we look into other materials like masonry unit, bricks, clay bricks particularly. This is a serious problem. So, we will look into other materials, and obviously as we shall see today, the cement is not the same cement what we understand, let us say about 50 or 60 years back, because today there are n number of cements, not one, n number of combinations of cements, right. So, therefore, you have the options of handling in a right manner as you wish. So, ordinary Portland cement, when I am talking of this, I am talking of ordinary Portland cement. You know, it is produced by burning calcium carbonate and then with clay, found in clay or shale, nearly about 1500 degrees centigrade. Material sinter and partially fused to form what you know clinker. So, some other course also we talked about this, and this clinker is cooled and ground to fine powder with some gypsum, resulting in ordinary Portland cement. This you know. So, you can see right from here itself there are two things you are doing. You are calcining this, as we call it calcination, and you know which will require some temperature, then you are fusing them to form this, right, fusing them to form this. So, of course, this I have mentioned earlier. So, production process, limestone quarrying and crushing, that would be there, other raw materials. So, first I think I was mentioning this, that you will actually select the quarries based on appropriate composition of limestone and clay. You can't bring them from two different sources and mix, the cost goes high up. So, this is what then it goes to crushing, and then other raw materials, then you add fluxes, you may have to add clay and shale. So, that makes you know after crushing, grinding and then grinding and blending of all these materials, that gives you final blend that is stored, and then this goes to the preheater and then to a kiln where it is burnt, gypsum is added, then the finishing grinding that is done, that is done. That is the production process of cement, that is the production process of cement, right. So, that is the production process of cement. So, let us look at some issues related to how much material I require and what I produce. First, let us look at that, and then we will look into how much energy I would require, right. So, this is of course schematically this is what it shows. This is a quarry. This is actually collected, transported through the dumper. So, you see every stage you may have to do blasting here, depending upon the situation, and then of course, you know this is basically collected, loader which will load it, and dumper truck. This goes to the basically grinding unit, from where it would be stacked somewhere, or some homogenization would be done, then stacked, then it would go to the grinding units, right. And then these are the preheaters, calciner, the kiln, and final product would come, something else you might be adding somewhere, the flue gases, right. And then the silos where it will be stored, the trucks loads it, transports it, etc., or ship it or whatever it is. So, this is the process that we are talking about. This is showing the preheating process, and this is a kiln details. The burner is on this side, downstream side, and as you know the hot gases go like this get clinkerization occurs here. So, here raw feed comes from the top, hot gases go from the bottom, and so on. So, this is the production. So, this is a kiln. It shows there are the burning occurs here, formation of compounds of cement, C3S, C2S, limestone decomposes. I am sorry, the raw feed comes from there, So, this is higher temperature, this is lower temperature, free water will move away, clay then decomposes, limestone decomposes, C2S and then C3S forms, right. This is cooling zone. So, dehydration zone, calcination zone, clinkering zone and cooling zone. So, that is what it is, and the temperature is shown 50. So, that is the process basically, that is the process of cement production, right. That is the process of cement production, right. That is the process of cement production. Okay. Okay. So, that is typically the, I think I might have, it might be there in another course or something, that is basically in the control room you see something of this kind. In the control room you see the screen of this kind, it is all automated, computer controlled and all that. They can see what is happening in every point, any chemical plant you go, it will be like that. So, this is the phase diagram, right, of cement. This is the temperature, this is the proportions by weight of the raw meal. You have initially calcium carbonate, quartz, clay minerals, etc., etc. So, this is, clay minerals will have low quartz and these combinations, iron oxides. So, the moisture goes away, right. So, moisture goes away, so it becomes a little bit dry. Then somewhere here this gets changed to high quartz, another crystalline form, and then this are the compounds form at different stages, liquid stage, finally cooled liquid, solidified, that is where the clinker is. This is at this stage, that is C3S forms, this is the C2S belite formation occurs or C2S formation occurs here, some free line. So, that shows the process again. So, I think we will break here and look into the more into the raw material of cement for a while, right. So, any questions if you have, I will take it right now.